In this video, we are going to learn everything related to data structures. We will see that what are the types and categories out there. Plus, we will see that what are the advantages and disadvantages of every single one of them. I'm going to visually draw each and every data structure, so you will have an idea that how that is actually stored in the memory and how it represents in the real world. Plus, we will talk about the scenarios where that data structure would be very useful, and I'm going to discuss the trade-offs between every single one of the data structures. So in my opinion, this video is going to be really helpful to a lot of people, and I hope that you also feel the same way. Let me know in the comments if you feel otherwise, and without any further delay, let's just get started. First, let's understand that what is actually data structure. Well, basically, if you have your computer, the most important piece of information in your computer is actually the data that you have currently stored. And with your computation, you are trying to actually solve some problem. So whether that problem could be that you just wants to browse through your Facebook feed, or you just wants to book a ticket for some airline, whatever it could be, you are essentially sending out and receiving bunch of different data packets, and you are doing all sorts of things. Data structure is the efficient way and mechanism to store these data inside the memory of your computer, or if your, let's say, some application is running in the cloud, still it needs to store the data. So this is a way that how the data is going to be stored. Now, depending on the storage decisions that you have made in this part, it can dictate that how, let's say that if there is some other third party who wants to access this data, how they are going to do it and how they are going to perform those operations. So that is why the way to structure the data becomes really critical depending on the exact specific problem that you are trying to solve. And that is why there is so much emphasis on data structures. And now let's see that what are the different types of data structures that are available to us. So the first type is actually quite simple. It is primitive data structure. And what do I mean by primitive data structure? These are the basic, most simplest data structure that are available. That includes stuff like int, character, and boolean, something like this. So all of these, they are predefined in any language you are trying to use: Java, C, C++, Python, whatever. This is the way that actually you can store the bits of information in the physical RAM or the hard drive of the computer using these. But we need to go a step higher, and we actually need to modify the structure that we are trying to build, not only just the what type of data that is going to be stored. And there comes two main categories. First is a linear database, and second is a non-linear database. So if we talk about the linear data, well, typically these are the more simpler yet very powerful data structure, where that in memory you can store in a single line. This thing represents arrays, then linked list, stack, queues, and there are a bunch of different sub portions, but these are the main linear data structures that we need to worry about. Then there is also another category for hierarchical data structure. And what do I mean by hierarchical data structure? Essentially, it has to deal with trees and graphs. So if you know that even inside any tree or graph, they are typically represented in some sort of hierarchical structure, and this is why they are categorized as hierarchical databases. Now inside the trees and graphs, there are also a lot of subcategories, but we are not going to talk about it right now. We are just focusing on the broader categories. Then there comes hash based data structures. So what does hash based data structures mean? Essentially, this includes the most popular hash table and hash set. So they actually use a different hashing mechanism to store the database and to work with it in quite efficient manner. So we will talk more about this in the upcoming sections. Then there are advanced data structures, and we are not going to tackle the advanced data structures in this problem, but let me know in the comments if you want to see these. If you want to know that which are the advanced data structures, basically it has to deal with segmented trees, then Fenwick trees, then disjointed set, sparse matrix, and spatial data structures. These are basically all the categories of different data structures. So arrays are one of the most basic and one of the most popular data structure out there. Essentially, arrays are a fixed set of memory bunch that is stored inside the CPU, where the number one, size is fixed. Number two, all of these values, they are indexed. So what do I mean by index? So currently in this array, you can actually see that we have the ability to store 4 different values, and these 4 different values can be stored in these cells. So in this case, if we have to reach to any particular cell, they are usually done using an index. So index typically starts with value 0 and go till the length of the array. So in this case, let's say that the value that I have currently stored in this position, I want to retrieve that. So in this case, I don't need to jump over all of these things and then reach to this position. I can directly call this array. So suppose this name of this array is A. I can just say that for this array A, give me the value that is stored at index number 2, and then I can retrieve this constantly. So in very quick manner. So number 1, it is fixed size. Number 2, retrieval is quite quick. And on top of that, all the values that I'm trying to store inside this array A, they all has to be of the same type. So what do I mean by same type? Well, let's say that in this array, I decide to store integer value. Then all of the values has to be some numbered values. I cannot store any of the character or boolean or any other values. Let's say if I create a character array, then all the values that I'm going to store inside the array are going to be based off of some character values. So I can store values like A, B, C, D, stuff like that. But in either case, they all has to be of the same type. So these are the typical properties of an array, and visually they look like a continuous block of memory that is in fixed size. Now let's see that what are the different operations we can do on any given array and how they behave in inside the memory. So suppose this is our array. So first operation we can do is insert the array or insert the value inside our array. So that is actually quite quick if we are only doing it within the bounds or within the size. This is the important topic. Let's say that this is the current array and we have the values that we can store. We can store 4 values at this time. So any place where we wants to add the value, let's say we want to add a value over here, value number 2, we can do it pretty quickly in constant time. There are no issues with that. All we need to do is just go to that particular location and add whichever value we want to. But the problem comes for the insertion when we actually go beyond the bounds of our array. Let's say that we currently have an array of size 4 where we can only store 4 values, but I want to store a 5th value. What would happen in that case? That our computer is actually going to create another array, and since this array was actually of size 4, so this time it is going to create the double size of the previous array. So not sure if I created an array with 8 length, but you can imagine that this is going to be of length 8. And in this case, the initial values, let's say this was 0, 1, 3 and 4. These were the values stored. So 0, 1, 3 and 4 would come over here, and then whatever the 5th value I was trying to store, that would come in this block. And same thing will happen until it runs out of space. And if it has to create a new element, then we will have to create an array with 16 values. So if we do the insertion within the given prefix size of the array, it is very quick. It can be done in big of one time. But if we have to expand the memory, then this operation becomes very expensive, and then this actually happens in big of n time, because first we will have to create a new array, shift all the elements that we had already stored into the new array, and then add the new element that we are trying to add. So that is why, remember, whenever you are using an array, make sure that you know the size and you stay within that size. If you know that at any position you are going to dynamically increase or decrease size, then don't use array. This is number one suggestion I can give you. But if you know the size, arrays are a great thing to do. Same thing happens with deletion. So let's say that if we want to delete some element inside the array, this is also quite quick if you know which element you want to delete. So let's say in this case we have the values 1, 2, 3, 4 and 5, and you know that on location number 2 the value number 3 is the one that you are trying to delete. If you know this, you can basically delete this, and in this case this is going to have null value, so no value will be stored in this memory bucket, but all the other places would have the subsequent values. So this is also being done in constant time, so you know that this is quite easy. Deletion. Next important operation we can do, that is traversal. And trust me, you are not going to encounter any array question where you don't have to traverse over the given array. So what do I mean by traversal? Let's say in the previous scenario, we have the same array where we have the values 1, 2, 3, 4 and 5 stored. Now you want to delete value number 3, but you don't know that where does 3 reside inside the given array. In that case, what approach you are going to take is that you are going to traverse over the entire array sequentially until you reach the value number 3. Now in this case, since this is a sorted array, you have some additional leeway to use a binary search in this case to quickly go over the array and do this in big O of log n time. But if the array is not sorted and you cannot use binary search, in this case traversal would take big O of n time. So for traversal you have two options. If the array is not sorted, then it takes big O of n time. If the array is sorted, then you can use binary search, and then that way you can accomplish that is big O of log n time. So both of this are really important, and you need to make sure that you know when you are traversing. So let's say in many questions you would realize that traversing is an expensive operation. So rather than spending this whole time, if you can try to sort out the array, and then you would be able to find the values quite efficiently. Same goes with searching, that if you have to search any element, first you would have to traverse over the given input, and I just explained that what sorting and not sorting would lead you to. So you would be able to search any value inside the array quite easily. Now let's see that what are the benefits or what are the advantages of the given array. Well, the number one advantage of the array is that random access is quite fast. And what do I mean by random access is quite fast? Well, I just showed you a couple of examples where inside the given array, if any middle point you wants to access, you can actually do it in constant time. So this becomes great use. Next thing is memory, how it is stored inside the memory. Because it is a continuous block of element, that computer already knows that how much space it is going to consume, so it can manage its processes accordingly. So this is a great advantage. And next big advantage is that it is quite easy to use. What do I mean by quite easy to use? Number one, for programmers it is quite easy because everyone can visualize that what does array look like, and they all can work with. Plus it stores the same data type values in quite frequently. So most of the time whenever you are designing your solution or trying to solve some problem, there is a very high probability that you are going to be dealing with the data of the same type, and then you can use an array to store it quite easily. Now let's focus on the disadvantages of array. What are the cons of an array? And the biggest con is that that was one of the advantages as well, that it is actually fixed in size and it cannot grow larger as your input grows. So only use array when you know that you are going to be remaining in the same bounds. If you have to increase the bounds, then don't use array. But there is actually an array list that we can use for any programming language that automatically provides this functionality. So it is a way to overcome that. But if you strictly speaking, if you are just using simple array, then because of this fixed size nature, don't use it. Why? Because insertion and deletion in that case is going to take big O of n times if you are increasing in the size. So that is one problem. Another problem is that because array is a fixed size element, and if let's say for an example that you allocated an array with like 50 values, but you are only storing 5 values inside the array, still this remaining values that you are not using is going to be consumed by your CPU. So that is going to be a CPU power wastage. So make sure that you don't want to be in the situation where you're wasting the precious memory and inside the array. And on top of that, searching is still big O of big O of n time or big O of log n time in either case. So these are the limitations of an array. But I hope that this gave you a broad enough idea that how does arrays work. And now let's move on to our next data structure, and that is linked list. So linked list is one of my favorite data structures, and there is a good reason for that. Basically, essentially, whenever we are talking about linked list is similar to array and also not at all similar to array. Why? Let me tell it to you. Essentially, in the array, you have the access, and you know, or the CPU knows that where the entire array resides. This is not the case inside the linked list. Inside the linked list, how it is set up is that it is something like the Jimmy or Better Call Saul from Breaking Bad. Why Better Call Saul? Because he was famous for knowing a guy who knows a guy who knows a guy. And same thing is with the linked list, because in the linked list you only have the access to the root node, and then in the root node you don't know that what are all the elements present inside the linked list. You don't know that where which element is stored or which memory location it is stored. All you know is that from this first node you would know that where does the second node resides. So first node would have the value that it is trying to store. So this can be any like integer or character or boolean value, or any class node that you have created. You can store it inside your linked list. And also in the separate portion of this linked list, it is also going to have the address of the next memory block. And same goes on and on, that next memory block is going to have address of the next memory block, and same way next memory block is going to have the address of the next memory block. So what would happen in the end is that in the end we would encounter, let's say that this is the end node of our linked list. Then in this case there would be one section that contains the information that we need, so that is useful to us, but its next node that is pointing to, it is going to point to a null value, and the moment it points to a null value, we would know that now we have reached to the end of our linked list. So if we have to represent it, let me say that this is currently an array. I'll show you the representation both in the array and also in the linked list. So if we are trying to store these value 1 2 3 4, they are continuously stored inside the array. Now let's see that how they are stored in the memory of the CPU. So suppose in the CPU, let's say that this block starts at value number 100, and then this block would start at 200, and then this block would start at 300, and this block would start at 400. So if we want to access this value number 3 or the position number 2 inside the index, then all the computer has to do is go to this cell or this bucket that is located at position number 300 inside the CPU of the computer. I'm just giving you this for the simplicity's purpose, but you would be able to understand what I'm trying to convey here. Same thing were to happen inside the linked list. Linked list would store something like this, that we would have our first node that contains the value 1, and let's say that this node is currently located at address 100. Now this node 1 would say that next node is actually stored at address 500. Now at address 500 we would have another node looking like this, and over here we would have two elements. So first element would contain value number 2, and then next node would have the address, and this address is and by the way this would be 500 node. Now this address could be 700 something, it can be any random number. Now at the 700 position there would be another node, and that node is going to have value number 3, and then it would have the address for the next element, and this can be again 200, anything can be there. And over here in the final we are going to have value number 4 stored, and then this next pointer is actually going to point to a null value, stating that there does not exist any value beyond this point. So this is how our linked list is going to look like. So now let's see, now we know that what are the characteristics of linked list. Now let's see that what are the subtypes of the linked list. And yes, you heard me correctly, that even linked list has subtypes. So first type is singly linked list, second subtype is a doubly linked list, and third subtype is circular linked list. So we are going to talk about every single one of them. Now what does singly linked list represent? Singly linked list represents the type of linked list I created over here, and as per the name you would be able to understand that any single node only has the address of a single node that is coming after it. So suppose you are located at this position number 3, you would not know that which node called position number 3. It could be possible that there is some other node as well that has, or let's say that this node 2 we want to replace. What we can actually do is that we can get rid of this node completely and not have this located at position number 700, or sorry, not have this stored at value number 500. We can actually create a new memory block, let's say at position number 400. We would update that memory block inside our first element, where we are going to store the value as 400. And now at 400 we are going to store value number 2 that would have the address of this node number 3, that it is located at 700, and at 700 we would still have this block. So now this linked list block is being called by completely different node than the original node it was already present. And this is the type of structure singly linked list has, that one node only has the single address, that is their next element, nothing more than that. But doubly linked list is slightly more intelligent and slightly more calculated than that. And what it has is that every single block looks like this, where we have the space for initial address and we have a space for the next node address, and then same thing happens at the next node. That next node also looks like this, where once again we have the address of the previous node and the address of the next node. So let's see that in action. Suppose these two has values 1 and 2. Values doesn't matter, we are just worried about the memory space. And let's say that this doubly linked list only has 2 elements, nothing more than that. So in this case, this first element, because this is the first element, we would know this because this would be the root node, and the root node is like the first element, so it does not have anyone else calling that root node. So this previous address of the root node is going to point to a null value. And in this case, the next address of this root node is actually going to point to this memory location where this node number 2 is located. So suppose this node number 2 is located at memory number 300, then this would contain the value 300. And same way over here, let's say that this value number 1 is located at memory 100. So in this case, because this 2 is a second node, it would have the address of its previous node, and address of the previous node is 100. So it would have that information over here, plus this 2 will have the information of where is the next node pointing to. So in this case, because linked list only has 2 elements, there is no next node. So this portion inside the linked list is actually going to point to a null value. But let's say that we decide to add one more value over here. So now this is no longer a null value, and we created one more block at the end with value number 3. So now in this case, and let's say that this 3 is located at address 400. So this 2 would have address 400. So it would be able to reach to value number 3. Same way, this 3 is in this first portion, it is going to have the address of this element. So address is currently 300. So it will have 300 in this first position. And then this next element is actually going to point to a null value. And this is how a doubly linked list works. So both have their own benefits and drawbacks. Well, good benefit about the doubly linked list is that you actually know and you can actually go back to your previous element. Meanwhile, in the singly linked list, you cannot go back to your previous element. So if you have to reverse the linked list or something like that, it becomes quite easy to do it with the doubly linked list. Now there is also the last one, and that is the circular linked list. This circular linked list is very similar to a doubly linked list, and the only difference is, and you must have guessed it from the name, that this node number 3, rather than pointing to next null element, it actually points back to the first element. So this portion would have the address of the very first element, and very first element in this case is value number 1. So it would have the address as 100, and 100 is the address of the first element. So that's why it is going to point over here. And same way, this node number 1 would not have the previous address as null, rather it would have the address of the previous node, and the previous node in this case is going to be value number 3. So that's why the address of value number 3 is 400. So this node is going to store the value of 400, and this is how essentially linked list works. So I hope that this explanation makes sense, that what every single type of linked list does. Now let's see that what are the operations you can perform and how they are being done in terms of that. So first operation we can do is actually inserting the element inside the linked list. So inserting the element inside the linked list is actually tricky. How it is tricky? There are actually couple of ways depending on where you want to insert, and the time and space complexity changes. So let's say that you have your linked list structured like this. Now in this case, if you want to insert some element at the very beginning of the linked list, it is quite easy. All you need to do is just add one more node over here, point that node to the previous first node, and previously your root node was pointing to this node, so delete that, and now mark this as your new root node, and that's it, you are done. So insertion at the beginning would be done in big O of 1 or constant time. Second option is that in the same existing linked list, rather than inserting in the middle, let's say that, rather than inserting at the beginning, let's say that you try to insert somewhere in the middle. If you have to do that, there would be, first let me show you how the insertion process would work. So the insertion process would work something like that first of all, we are going to get rid of this portion. We are actually going to create a new node. So let me create a new node that looks like this. Now in this node, I'm going to point it over here. Meanwhile, previously this was pointing to this node, and this address I'm going to pass it on to store over here, and this is going to point over here. So this whole portion, this whole process is actually quite simple and quite similar compared to an array, where if you run out of space, you might have to create an entire new array. In linked list, because this is a dynamic data structure, it can grow and it can shrink in size without the worry of how the computer is going to allocate that. Computer is going to find whatever the empty space it has, and it is just going to allocate that to the existing linked list. So this portion, like doing this, is actually quite easy. This can be done in big of one time, but there is a big problem with insertion in somewhere in the middle. Why? Because you only have the address of the very first block. So before inserting, you will actually have to jump to that point before you can actually add that value. So that is why if we are inserting somewhere in the middle or somewhere in the end, in either case, we would have to reach to that node first before we can add that value. So that could take big of n time. So insertion at the beginning would usually result in big of 1 time. Somewhere in the middle or at the end, it could take big of n time. Same goes for deletion. Again, deletion process is quite simple inside the linked list. How you actually delete a node? Well, let's just use the same example. Let's say I want to delete this node. So all I do is I get rid of this node, the previous address that it was pointing to this node, rather than pointing from this node to this node, I would actually ask this node to point to that address, and that's it. Now this block is no longer accessible because it has been emptied out, and our linked list still functions the way it does. So this particular deletion only takes big O of 1 time, but again the same problem arises that if we want to delete something from the middle or something from the end, first we will actually have to get to that point before we can do that. So that would take big O of n time. Now let's talk about traversal. So traversal, you must have got an idea that how we can actually traverse through a linked list. You only have the access to the first element, and through first element you will go to next, and through that you will go to next. So there is no way for us to access any middle point at ease. Whenever whatever value we have to access, or whatever value we have to do it, we will actually have to traverse through it. So it is going to take big O of n time, and there are multiple different ways for traversal. You can actually traverse using loops and for loops and while loop and do while loop, and there are all sorts of way. Plus there are some predefined methods in any smart languages as well. And same goes for searching as well, that if we have to search for any element, you would have to first traverse first, and in this case you cannot use binary search tree because there is no fixed memory size. So you will have to only do it sequentially. So searching only takes big O of n time, nothing more than that or nothing smaller than that. Okay, now let's see that what are the typical use cases where we can use this linked list. Well, use cases are actually quite simple and quite similar because this is actually a dynamic size. So wherever you need a data structure that automatically grows as per the demand of the data, or automatically shrinks as per the need of the matter. Linked list is a great way whenever you are trying to deal with dynamic modification of the memory. Second thing, as we already told that insertion and deletion are actually quite simple. So if you know that you are going to do a lot of insertions and deletions at the beginning of the linked list, and then all the add values you are going to append in the backend side, then this becomes a great option to implement. Plus, linked list can be the base implementation for a lot of other data structures as well. So what type of other data structures you can actually implement using linked list? You can implement stacks, you can also implement queues, and you can do like priority queue, priority stack. You can also implement heap using two linked lists. So I'm not going into much detail, but know that whenever you are being told to implement any other data structure, with some of the primitive data structure, try to think of linked list first, because they are going to be really easy and really simple. Memory management is quite good in terms of linked list. Why? Because computer does not have to allocate a single chunk of block like it did in the array. All the values can be dynamically arranged. So let's say that computer currently has memory 100 free, so it will do that. Then it has a memory block available at 1700 locations, so it can do that, and still it won't impact the performance of the computer or CPU. So that is really good. On top of that, you also have the option that using doubly linked list you can actually navigate into the two directions. So you can also do that. So navigation on multiple fronts can also be possible. Plus you can also use fast and slow pointer. So one pointer would do sequentially, meanwhile the other pointer would jump like into the double the speed of the existing linked list. And they actually have their own use cases as well, which you will see many times. Now let's see that what are some of the disadvantages or scenarios where you don't want to use linked list. So number one scenario such like that is whenever you are dealing with fast access. So if you have any need where you need to access any element pretty quickly, you won't be able to do it, because in the linked list you only have to jump through all the hoops before you reach to the element you are trying to do. So in that case it is not very much ideal. Plus if you know that size is going to be fixed and you are trying to implement a linked list, then linked list would be a little bit slower. So in that case it would be more recommended to use arrays or something like that, because most of the operations on the linked list are being done in big of n time. Meanwhile in the array you still can do some fast access. So these are the two data structures. Now let's talk about stacks. So what does a stack represent? Stack is quite simple data structure. Stack is typically, let's say that you have a table. So on table, if you are trying to put down all the dishes, how you are going to put them, you are going to put it one on top of the other and then one top of the other. So if you, whenever some other person wants to access that plate, they won't be able to take a plate that is currently located in the bottom. They can only take the plate that is currently located at the top and nothing more than that. So stack actually follows the principle of LIFO. So what does LIFO means? LIFO means last in, first out. And what do we mean by that is that this, let's say that currently we have only a single plate that is currently present. Now I decide to put one more plate on top of that, and then I decide to put one more plate on top of that, and then I decide to put one more plate on top of that. So whenever some person comes in, that person would only have the ability to take the first plate. They are not going to go for the bottom plates, otherwise all the plates would fall over. So in that case, this blue plate was the last plate that we put in. So last plate that we input, and that became the first plate that come out. So that's why it follows the principle of LIFO. This is really good. And this is the whole logic, or this is the whole concepts of basically stacks. Now let's see that what are the different operations we can do on stacks and what is going to be their meaning for that. So in the stack, first operation we can do is actually push. So what do we mean by push? Now let me draw an example. I'm drawing this bucket of memory. You can imagine that we would be able to put stuff in there from this way, and when we have to take the stuff out, we will also take out the stuff from this way as well. So whenever, let's say that currently this is completely empty. Now I want to put one element over here. So let's say that I want to put value number 1 over here. So 1 I'm going to put in. So 1 would only be stored at the bottom. It cannot store at the top because we still have memory left, and this is the way it is going to store. Okay, now I stored value number 1 over here. Now what I'm doing is I'm using a push operation. So I push a value down. You can think it that way, so that would make more sense. Now let's say that if I want to push value number 2, so again I would put value number 2 and it would be stored like this. If I want to put value number 3, so again I can put value number 3 and it would be stored like this. And this is how our stack is going to look like. So this is one operation, that is to add values to it. Second operation is to pop values out or take values out. So pop means we are taking value out. So let's say that this is the current state of our stack and we decide to use pop operation. The moment we use pop operation, it is going to pop the first element that is currently present. So in this case, now 3 is going to come out. So we would have 3, but in the array, or sorry, in the stack, we would not have value number 3, and the pop result would give us the value number 3, that this is the element we popped out from our existing stack. If we use pop element once again, then in this case, it is again going to pop out value number 2, and 2 would not be present over here. Same way, if we use pop once again, then it would generate or take out the value number 1, and because it took out the value number 1, right now there are no elements inside the array. If we decide to pop one more time, in this case it is going to give us the answer null, saying that there are no elements inside the given stack, so we cannot pop anything out. Now let's talk about one more operation, and that is called peek. So what does peek means is, peek means that we are just peeking into our stack. So suppose in this example, we decide to push more values in, and we decide to push 1, 2, 3, 4 over here. Now in this case, the moment we use a peek operation, it is not going to take this thing out, but it is going to see that what is the value located at this place. And in this case, because the located value is value number 4, it is going to say that currently the very first element of our stack is actually value number 4, but it will not bring it out. So that is why stack is a really good data structure to use. Now let's see that after knowing these operations, and by the way, all of these operations, they happen in big O of one time, nothing more than that. So everything is constant time, but there are only a limited number of things we can do. So that's why even the use cases or the advantages for stacks are also very limited. So what is the first advantage that we can think of for the stack? Well, if we have to balance something out, what do I mean by balance something out? Well, anyone who has done some sort of programming, they know that we have to deal with lot of open and end brackets. It can be in the many different shapes, but it has to be done in the same sequence. So in this case, first I open a square bracket, then I open a circle bracket, and then I open a curly bracket. So they has to be closed in the same fashion as well. Now, if there is a match or there is a mismatch, if I want to identify that, stacks can be a great way for us to know that how it was opened and how it was closed. Why? Because let's say that currently in our stack, we are pushing the values one by one. So very first time we opened the value of a square bracket. So we are going to add a square over here. Then we opened a circular bracket, so we add value circular over here. Then we add a curly bracket, so we are going to add an open curly bracket over here. Now next thing, we decide to start closing out the brackets. So the moment we close out a bracket, we can check that okay, this is a closing bracket. We can actually pop one value out and compare that we are closing the same bracket that is currently open the last, because in the brackets it has to be done in the reverse order. So that is why the last bracket that was opened would be the first bracket that we are going to close. So the moment we encounter a closing bracket, we would pop one element out. If both are of the same kind, then it is great for us. So we can pop this out. Then later down, we realize that we are closing one more circle bracket. So that time we would also pop one more element out. And because we found out that this was an opening circle bracket and we have a closing circle bracket, so there is a match, which means good. And same goes for the rectangle bracket. So whenever we have to validate parentheses or find these kinds of stuff, stacks are a great way to do it. Then also one more thing stacks are good at, and that is to do an undo mechanism. So what do I mean by undo mechanism? Well, if you are browsing through your Chrome or your Internet Explorer, anything, the moment you hit this back button, it is going to take you back to the previous page that you were at. How does it know that? So that is typically done using the stacks. So let's say that currently you are doing web browsing. So first you opened the Facebook page. So the stack would have an entry of Facebook over here. Then from Facebook you decide to go to Instagram. So then stack would have the next entry as Instagram. From this Instagram you decide to go to YouTube. So stack would have another entry called YouTube over here. Now from this YouTube you decide that you want to undo or go back to the previous place. So it is only going to pop out the value from the YouTube that was the very last element. And since it found that last element was an Instagram page, it can actually go to that Instagram page. From Instagram, if you decide to do undo again, it will again go back to that Facebook page. But let's say from Instagram you decide to go to some other application, and from Instagram you decide to go to a Uber page. So currently you are at Uber. From Uber you go to Netflix page. So again you are at Netflix. Same way from Netflix, if you try to do undo, it will only take you to Uber and then it would take you to Facebook. So essentially undo mechanism is great using stacks. So that is very good whenever you have to do it. Plus wherever you have to do like a reverse Polish notation, that is very similar to that evaluating different expressions. So expression matching is also quite good. Backtracking is also quite good. It is very similar to the undo functionality. So these are all the scenarios where you should definitely use stacks. Now let's talk about one more linear data structure, and that is queue. So queue is slightly different than a stack. You can consider the queue to be a distant sibling of a stack, because notice that in the stack we have the mechanism where we are filling in the data from one end and we are taking the data out from the same end, nothing more than that. But inside the queue it is going to be slightly different. In this case, queue is going to work like a normal queue that we have, and this portion is not going to be present over here. So basically if we enter one value from this side, the value is going to come out from the other side, just like it works in the actual real life queues. So queue, we can consider that it follows the principle of FIFO. So what does FIFO means? That first in, first out. And in this case, let's say that currently you are waiting to make your driving license, right? So here let's say that there are people sitting who are the officers who make the driving license. Now there would be long queues where all the people are standing, and the people at the very first would be the people who came in the earliest, and then the line started growing up. So if this let's say this officer decides to call someone to make the license, they are only going to call who is the person who was the very first person who came inside the queue. And that is why queues are being used. So essentially queues are there to manage a sequential task, that in which sequence things happened and in which sequence it is going to store the values. Understandable. So I hope you are able to understand what does a queue represent. Now let's see that what are going to be different operations that we can do inside the queue. So first operation we can do is, let's say that currently this is your queue. Now I'm drawing it as an array, but you could be able to imagine that this is actually a queue that I'm trying to draw, and let's just keep these two portions open for the values coming in and values coming out. Now in this case, we are, let's say that very first time our queue is empty, so we want to add the data. So for that we are going to do enqueue function. So if we do enqueue function, let me add value number 1 over here. So I add value number 1 right now. Now let me decide that I want to add value number 2. So what would happen is that this 1 is still going to be remain the very first value that it needs to come out. So essentially we can actually consider this 1 would be the very first value and 2 would be entered just before that. Then we decide to add value number 3. So in this case 3 is going to come out over here. Same way, let's say that we decide to add value number 4 in this case. So once again 4 is going to come out over here. So this is how your queue is going to fill up. And good thing about queue is that this is also a dynamic property. So you don't have to specify the size of the queue, it automatically grows and you can manage that. So that is pretty good. Now let's say that after filling up the queue with all the values, you actually want to keep people out or get stuff doing. So for that we did enqueue. Now you need to do dequeue. So dequeue means that we are kicking people out or we are getting rid of things. So whenever we do dequeue, essentially this first element would be the very first item that comes out. So if we do dequeue, then we would have value number 1, but this 1 would no longer be stored over here, and this 2 would become the very first element that is currently present inside the queue. Now if we decide to do dequeue once again, in this case 2 is going to come out. So 2 would no longer be placed inside the queue, and we would get the answer for DQ operation as value number 2. So this is how NQ and DQ are going to work. Same as the stack where we had the peak function, we also have the peak function inside our queue operation as well. So let's say that for this given queue, if we decide to use peak operation, it is not going to kick 3 out, but it would be able to say that 3, if we were to kick out some element, or if we were to do a DQ, then 3 would be the very first element that would come out. So peak would give us the answer 3. And once again, let's say after doing peak, let's say we decide to DQ couple of more times. So if we do DQ 2 more times, then 3 and 4 would come out. Now if we do peak, then in this case the answer we are going to get is going to be 5. So this is how these are the different options that works for queue. Now queue is not as simple as stack, and queue actually has couple of different 3 different variants. So let's talk that what are the categories of queue. So the number 1 category of a queue is a circular queue. Second category of the queue is a priority queue, that is pretty important. And third value of the queue is actually double-ended queue. So let's talk about each one of them one by one. So circular queue, as the name suggests, it is not in the single fashion, but actually rather a circular fashion. So all the elements that we keep on inserting actually gets added one after another, and they have some very specific use cases. So even though, so let's say that very first element we add is value number 1, next element is 2, 3, 4, 5, 6, 7, and we keep on adding all the values again and again and again. Then this value number 13 is just going to be very next to value number 1. And but in this case as well, still the peak, if we do peak, then it is always going to show value number 1, because 1 was the last element that came inside. So circular queue you would be able to identify, but there are very few specific use cases. Now let's talk about priority queue. Now priority queue is really important because this very much represents some real life scenarios. Now let's go back to our example where there is one DMV driver or one officer who makes the driving license. Okay, so this is the driving license making officer, and he is currently sitting behind his desk, and there are a lot of people queuing up. So I'm marking all of these people who are queued up. Now technically this would be the first person that needs to go to this queue, and that needs to complete his driving license procedure. But at that same time, this officer notices that there is a person who is currently in the wheelchair. So because this person was not in the behind the queue, but still that person would get priority because he is handicapped and he cannot go no longer there. So first he is going to process these while keeping these people in the same sequence inside the queue, and then he would start calling these people one by one. So let's say that officer completed this person with the wheelchair, then that officer also completed these 2 people. Now technically this person that is currently present, let's say that person C is present, who should be going next for the driving license, but at the same time there comes a pregnant lady. So in this case, once again, because the priority of pregnant lady trumps this normal person, pregnant lady would be the first person who is being called. So this is how priority queues work, where depending on certain cases or certain conditions, you can define that certain values are in higher priority compared to other values. So that is also quite good. And now let's talk about what is the double-ended queue. So double-ended queue is actually the combination of queue and stacks. How it is combination of queues and stacks? Well, in the queue we know that first in first out. So let's say that we have the values 1 2 3 4 5 come in, and this is first in first out. But in DQ we also have the option to remove the last in element that came in. So in this case you can also remove the value that came in last, or you can also remove the value that came in first. So you have the option that if you want to do sequentially in the normal queue, you can remove value 1 2 3. But let's say after removing 1 2 3 you decide that I want to remove from the end, then you would remove value number 5, and then you would remove value number 4. So this way these are some of the different variants of the queue. Now let's see that what are the use cases where you need to use queue. So number one system is that wherever you have to keep track of task, queue are the great place to do it, because queue knows that okay, this task was the first task that came in the sequence after this one, and you can do it. Let me give you a real life example. Let's say that there is an office, and office has lots of people, lots of employees. Now amongst these employees, there is only going to be one single Xerox machine or photocopy machine where you can take out the printouts. So let's say that person A first send out his or her data to be printed out. Meanwhile, the printing job is not done. Person B and C and D, all of them send out their printing jobs as well. So at that time, we can have a queue that maintains this system, that after this person A's stuff is done, we can use person B. After that, we can use person C's, and after that, we can use person D's stuff and print all of these items. So this would be a normal queue scenario. In this case, we can also have a priority mechanism as well, that let's say the VP of the company wants to get something printed out, then for his stuff needs to be taken care of very first. So let's say that this A's stuff is almost about to be done, then rather than taking on this value number B, it would actually take this VP, complete his job or his or her job, and then it can also start doing with the value number B. So this would be a great way for you to implement like any sorts of task sequencing mechanism, and in itself it can has a lot of different options, because task scheduling, we see it in day-to-day basis, like we see token system in all the offices. Now next thing is, let's say that if you want to do a round robin scheduling, so in this case as well, queues are very friendly and very useful. You can also use a circular queue in this case. Plus, if you want to create a buffering mechanism, so we know that what buffering is, that in the YouTube, if you're trying to see something, there are always the two arrows that are always chasing each other. So there would be one arrow over here, and there would be another arrow slightly above that, that is actually going to buffer stuff. And when this arrow crosses, everyone loses their mind. But in this case, even in order to implement the buffering system, we can actually use queue, that these are the data chunks that we are going to process inside of any streaming service. The first and one of the most popular data structures out there is actually trees. So trees is not your everyday looking array or linked list. It's actually completely different. First thing, it is a hierarchical data structure. Second thing, for the trees, you actually have to consider some terminologies. So typically a tree looks like this, where it has a node. In this node, you can store some information. So that information can be anything. You can store an integer value, you can store a character value, or if you want, you can store some class values as well. So let's say that you created a class called person, and in that class you have that first name, last name, and date of birth. You can fill out all of those information in this node. But apart from that, on top of storing all of this information, let's say that you store that information in the majority part of the given tree node. In the rest of the part, you actually create the connections that it is connected to with other nodes. And this is really important. So one single tree, you only have access to the root node, but from this root node, you can actually connect to multiple places inside the given tree. So you can actually be connected with two more nodes that are below that. Under one of nodes, you can be connected with 3 more or 4 more or any more number of nodes. This node maybe only have one node, then this node has another node, and this is how typically a tree progresses. So when we are talking about trees, we will have to first define few important things. So I already told you the number one thing, that what a node is. That node is basically the portion of tree that contains data, that contains important information. Now next important information for that a tree needs is an edge. And what does an edge represent? So if we see or take a look at this picture, edge is essentially the portion that connects any two node, and there needs to be some relationship between them. So typically in a tree, you would always see a relationship like this, where a tree is always under some other parent tree. So in this case, this root node is actually a parent node for these two subsequent nodes, but also at the same time, let's say that you have 4 more nodes over here. Then in this case, for these nodes, this becomes a grandparent, and this becomes these two nodes becomes parents for these subsequent nodes. So there is always a parent-child relationship, and that relationship is typically defined through an edge. Next, we need to discuss that what a root means. So root means the node that supersedes all the nodes. So essentially the greatest grandparent, essentially the very first node that becomes your entry point into the tree, and this is defined as the root node. Now let's talk about that what does a leaf node means. So leaf node means that the node that does not have any children. So let's say we have a tree that looks like this. In this case, we currently have a node. This node is by default the root node, and this tree is connected with these two edges to these two children. But these two children does not have any subsequent children of their own. So in this case, these two nodes actually becomes the leaf node that we are trying to explain. Now let's talk about the concept of depth. Now what does a depth means inside a tree? Essentially, for any given tree, it is always placed in the layers, that one root node has some children, then these children have subsequent children of themselves as well. There can be n number of children. For the simplicity's sake, I'm drawing two children for every single parent, but there can be n number of children. And in this case, we can see that currently this root node is actually located at depth 1, or you can also consider it depth 0, depending on what type of situation you are tackling. They are just numbers, but they would be the initial depth. And then with every level you go down, the number of depth increases by 1. So in this case, this is located at depth 1, this is located at depth 2. So essentially depth can also be considered as level of parents or children that each one of them has. And very close and very similar concept is of height. So height basically defines that how deep a tree goes. So in this case, from the root node, we actually go 2 levels down. So we can consider the height of this tree to be 2. Same way, from any single separate node, you can also calculate the height from that position as well. And in this case, the height would be 1 if we consider this smaller subtree of a tree. So these are the different terminology that you have to understand before we proceed with what a tree is. Now let's try to see that what are the different types of trees that are available. And trust me, there are a lot of types of trees. So first, let's just start with the simplest trees, and that is binary tree. Now what does binary tree defines? Well, we all know the meaning of binary. Binary means either 0 or 1, which means it means 2. So binary tree means that every single root node has exactly 2 children. So in this case, this would have 2 children. Same way, these subsequent nodes would have 2 children of their each, and so on and so forth. And until we run out of the level. So in this case, let's say that this has 2 children and that's it. So this is a binary tree. Why? Because by definition, every single parent has exactly 2 children or no children at all. So, and that property is followed across all the nodes. So binary tree is what you are going to encounter mostly in your typical interviews, and very closely, and a subset of this binary tree is actually binary search tree. So what does binary search tree means? That it follows all the properties that a binary tree has, that every single node has exactly 2 children or no children at all. But on top of that, the binary search tree has an additional property where the values that are being represented in those binary trees, they are actually sorted with the condition that everything on the left is actually less than everything on the right. And this property is followed throughout the entire tree. So let me give you an example. Let's say that we currently have a tree that looks like this, and currently the value of this root node is 7. Then it can only have children where the scenario is that everything on this left subtree has to be less than 7. If it is everything on this left subtree is less than 7 and everything on the right subtree is greater than 7, in that case we can define this as a binary tree, or sorry, binary search tree. So let's say that we add 2 more nodes over here, and these 2 nodes define the values as that this one is value number 5 and this one is value number 8. So far this follows the property of a binary search tree. That is good for us. Now let's just take it one step forward as well. So we have two more child over here in this case. So in this case, let's say that the value of this child is 3 and again value of this child is 6. Is it still a binary tree? Yes. Why? Because let's follow the same property. Currently, if we consider this parent node, then this becomes the left subtree. In left subtree, all the values are less than value 7. So that is good. Now let's consider this node. So this node is 5, its left is 3 and its right is 6. And that is also followed because left subtree is less than 5 and right subtree is greater than 5. So both properties match. Same way the right subtree is currently greater than 7. So this property also matches. So in this case, this would be a binary search tree. And binary search tree has lot of potential and lot of application. You can actually use it for sorting, or you can use it for to store data or to go hierarchically down. So we will talk more about this when we start talking about various scenarios where you can actually use the tree data structure. Now there is one more data structure that is called AVL trees. So what AVL trees is, that AVL tree is actually a special kind of tree where not only it is a binary tree, but apart from that, it is also a binary search tree, and on top of that, it is a balanced tree. So what does the balanced tree means? So let me give you first an example of a balanced tree. Balanced tree is any tree where all the nodes on the left side of subtree and all the nodes on the right side of subtree are even. So in this case, let's say if I have a tree like this is a balanced tree. If I have a tree like this where left node has 2 subnodes and right node also has 2 subnodes, this is also a balanced tree. So any symmetric tree is basically balanced tree, and AVL trees contains all of these 3 properties. Yeah, so that is about AVL tree. Then there are all more specialized trees, that is red black tree, and there is also B trees. But these are just too higher of the concepts, but I'm just going to give you an example that red black tree is actually a tree that has separate colors. So some nodes are defined in a certain color and the other nodes are defined in the certain colors, and depending on their positioning, the colors are maintained. So whenever you try to add new value, it automatically maintains the colors and it automatically generates that what should be the next subsequent value based on those coloring groupings. So the red black trees are great at sorting various items and various operations depending on the color property. And B trees are multi-level, balance and sorted tree data structure that can have more than two children. So it is actually much more complex topic, and in its own it has actually a lot of things that we can think about, but we are not going to go deeper because that would be a topic for much higher level. I just wanted to give you a brief overview for that. Now let's see that what are the operations we can do on a tree. So the operations are quite simple. We can do like searching, we can also do sorting, we can also do deletion and insertion, all of those things, right? But in order to do that, we actually have to traverse over the tree all the time. And the most important operation that you will have to learn about is that how the traversal works inside a given tree. So actually for trees, there are typically 3 different ways you can traverse over inside the given tree, and that in order traversal, pre-order traversal and post-order traversal. So how each and every one of them is going to work, well, I actually have a separate video on that, but if you want, you can just check what I'm trying to explain right now. What in order traversal means is that first we are going to visit the node, then we are going to visit the left child, and then we are going to visit the right child. Pre-order means that first we are going to visit the left child, then we are going to visit the node, and then we are going to visit the right child. And post-order means that first we visit left, then we visit right, and then we visit node. So let's see this in action. Suppose we are given a simple tree. So I'm currently drawing a simple, most basic tree, and we will go through its values, right? So let's say the values are 1, then on the left is 2, and then its right is 3. And also on the right is 4, and on the left is 5, and on the right is 6. Let's say that this is the type of tree that we are trying to generate. Now let's see that what would be the in order traversal would be for this type of tree. Well, of course, first we are going to visit the node. So node in this case is going to be the root node, and that is going to be 1. So the very first value we are going to go through is going to be value number 1. Then we are going to see all the left subtree. So currently for the left subtree, it only has node number 2. But again, at node number 2, we are also going to visit this. And then after visiting, now currently for this node number 2, it does not have any left subtree that we can visit. So we are going to go into the right side, and on the right subtree, we have value number 3 that we haven't visited. So we are going to visit node number 3. After that, again, we are going to repeat the same process. Now in this case, we already took care of this value, and this value. So now even for node number 1, we are going to go to the right subtree. But for right subtree, again, we are going to apply the same logic of node, left and right. So once again, we are first of all going to visit node number 4. And after that, we are going to visit node number 5, and then we are going to visit node number 6. So we took care of all the nodes. So this is how the traversal works for in-order traversal. Now let's do the pre-order traversal. And inside the pre-order traversal, it's clearly see that we need to go to the left as much possible as we can. So from the initial node, do we have a left subtree? Yes. In the left subtree, we are going to go to this node. Now, does this node has any left subtree that we haven't checked? No, because this does not have a left subtree, then we can visit the node. So while visiting the node, the first node we are going to visit for the pre-order traversal, let me just write it over here. So the first node would be node number 2. Now the next node we are going to visit is going to be the right subtree of this node. Now for this 3, it does not have any children, which means we will have to visit this node. So we are going to visit node number 3 first. After visiting these two, now for this node number 1, we took care of the entire left subtree. So we can actually visit node number 1 now. After visiting node number 1, we need to take care of the entire right subtree, but again with the same logic of left node and right. So again, we are at this position. Now this does have a left node. So we are going to visit 5 first, then we are going to visit the node, and then we are going to visit node number 6. So this would be the pre-order traversal for the given tree. Now let's see that what would be the post-order traversal for the given tree. So in terms of post-order traversal, it is going to be actually quite simple. Again, using the same logic, we need to first go through every single left node, then we need to go through every single right node, and then only we will visit the existing node. So currently for this 1, it does have a left node. For this 2, it does not have a left node, but it does have a right node. So we are going to visit node number 3 first. So in the post order traversal, the first node we are going to visit is going to be node number 3. Then the next node we are going to visit is going to be node number 2, and then we are going to visit node number 1. No, we are not going to visit node number 1 right now, because node needs to be visited in the end, and it still has right subtree that we haven't checked. So now we are going to visit the right subtree, and this portion now becomes the node. And for this, it also has a left node. So now we are going to visit 5, then we are going to visit 6, then we are going to visit node number 4. And after completing both of these portions, we are going to visit node number 1 in the end. So this would be the full traversal for the given tree, the in order, pre-order and post-order traversal. This is the most trickiest thing to understand for any single tree, and I hope you find it useful. Now let's see that what is going to be the searching, sorting, deletion and insertion for the given tree. So let's say that searching. If we are given a normal tree, then the searching is for sure going to take big O of n time. But if we are given a binary search tree, in that case searching would be big O of log n only, because every single iteration we would be moving half of the element on one side, and we can focus steadily on the target. So that is why binary search trees are so popular. Now let's talk about sorting. So for sorting, actually if we are given a binary search tree, then sorting is actually constant, big O of log n time, because it's quite easy to do. We only need to traverse over the given tree, and for many sorting algorithm, binary search trees are being used. Deletion, if we know which node we have to delete, then it's a constant time deletion operation. But if we don't know the node and we have to search first, then it becomes big O of n or log n, depending on what type of tree we are given. And same goes with the insertion, that if we know that we can insert any randomly, then it's big O of 1. But if we cannot do it and we have to insert it at specific location, then it's big O of n or big O of log n, depending on where we are trying to insert and what type of tree we are given. So this is everything you need to understand about trees. But now let's see that what are the uses on how and where we can actually use trees. So number one use case for a tree is typically a database management system. Why database management system? Because number one, binary search trees, then AVL trees, then red black trees, then B trees, all of these are huge and very powerful in separating all the elements. So that's why they are quite popular whenever you are trying to build a database. On top of that, they are really powerful when you are trying to index all the values, and indexing and enabling fast data retrieval can only be possible using trees. If you have to use anything for file systems or file management, so because tree, they are already in hierarchical nature, and whenever you see your Windows path or your something, you will always see something like C drive. It has a file called programs, it has a file called Java, it has a file called bin, something like that. So this is a parent child relation where every single node is connected with the other node, and you can actually go over that. Plus, if you want to create like a syntax trees, you can also do that using the trees. Why syntax trees? Because let's say that if you are trying to build a scenario or a compiler, something where you want to show that what class is connected with what other class, and you are trying to avoid any infinite loop scenarios, so in that case tree data structure would be a huge help. And on top of that, you can actually use trees to build priority queues as well. So this is also a very good benefit to use. You can actually do that using heap, and I won't be explaining the whole concept, but just know that this can be done. If you want to know more information about heap, I have also made a separate video on that, so you can go and check it out. Now, one important thing about trees is that it is a hierarchical relationship, and you would never encounter cycles in either scenario. Everything is going to be connected with each other, but there won't be any cycles. So because there are no cycles, we can actually define trees as the way they are, and there are so many operations that we can do. But if there were to be cycles, then there would be completely different set of considerations that we would have to keep in mind. And that is where the concept of graph actually comes in, where graph is a very similar data structure to a tree. And if we just talk about the terminology that we are going to use in the graph, even in the graph we are going to have a node, but in the graph we can also define node as a vertex, and that essentially represents the same circular dot that I just mentioned, where you can store all sorts of information like integer or character boolean or class value or whatever you want to store. You can store that inside. But on top of that, apart from that node having that important data information, it also has the information of other nodes that it is connected to in the current system, and those other nodes can be n number of nodes. On top of that, those other nodes can also be connected internally as well. And there are some scenarios where one node is connected with another node, but another node is not connected with that node, and that node might be connected with some other node, and that some other node might be connected with that node as well. So there are a lot of different ways graphs can work. Now, one key difference between a tree and a graph is that graphs can be cyclic in nature. And what do I mean by cyclic? That let's say that you have a node that is connected with another node. It could be possible that is also connected with another node, and that is also connected with the previous node. And this type of configuration would not be present inside a tree. This can only be present or prevalent inside the graph, and that is the biggest difference between trees and graphs. And that's why they have their own entire set of different considerations and connections. So now let's just go back to the basic terminology that we need to understand. First, we understood that what a node or vertex is, or vertices is. Next thing that we have to consider is the edge. And edge is it means the same thing, that is the connection point between any two values that are connected with each other. So edge means the connecting points. Now there is also the concept of adjacence. Adjacency or adjacent vertices. What do I mean by adjacent vertices? Let's say I have a graph that looks like this, and in this case currently let me mark the values as A, B, C and D. So in this case, if I consider this node number C, I can say that node D, node B, and let's mark this node as node E. So B, D and E are actually adjacent nodes to this node C because they are directly connected with an edge. But If this node is not actually connected with vertices, then in this case, this node C and A are not adjacent nodes to each other. So this is what do we mean by adjacent nodes. Now there is also a concept of degree inside for any single vertex. And what does a degree means? That degree means that how many number of vertexes or connections that every single node has. So let's say if I have a graph that looks like this, in this case I have node A, B and C. So I can define that this node only has one edge, so I can consider the degree of this node to be 1. In this case, for this B, it has the degree of 2, and in this case, this C, it has degree of 1. Now there is also another concept of the total degree depending on the incoming and outcoming edges as well. And where does incoming and outcoming edges comes to place? Well, we will talk more about that when we discuss the type of graphs. But remember that graphs can have a functionality where one graph is connected with another graph, but another graph is not connected. So in this case, if we have a graph like this where A has an edge leading to the B, but B does not have an edge leading to an A, which means from A we can actually go to B, but from B we cannot go back to A. So in this case, A would have a degree of 1, but B would have degree of 0 in this case. So that is the difference between these two, this concept of degree for the graphs. Now let's see that what are the types of graphs that we can deal with. So number one type of graph is a directed graph. And what does a directed graph means? That I just showed it to you, that this is actually a directed graph where one node is actually connected with another node, but it is not, the vice versa is not true. And the directed graphs can get really complicated as well. It is not always going to be this simple or this similar. And it could also be possible that there could be hundreds or even millions of nodes that are connected with each other in this fashion as well. Where we would have various degrees and various directions happening amongst different vertices. There could be undirected graphs as well. And undirected graphs are actually a graph where two nodes share a common edge. So in this case, rather than treating it as a single edge, typically this is used to be like this, where node A has an edge leading to node B and B has an edge leading to node A, which means from B you can also come back to A, and from A you can also go back to B. But in this case, typically we only show them using a single edge, and whenever there is an edge without an arrow, it defines that both nodes are connected with each other in the simplest manner, and there is a bidirected connection or an undirected connection. Now there is also a concept of weighted graph. And what does a weighted graph means? That let's say that you have different nodes, and different nodes had different connections, and different connections have edges, so edges carry weight as well. Let's say if I'm trying to plot a graph of a city. Now in this city, this node represents the Young Street, and this node represents the Main Street. Now these two streets are being represented, and there is, let's say there is also third street called Queen Street. Now there is a graph that looks like this, but in this case it could be possible that this graph I'm defining, this is defined as a road. So it could be possible that from Young to Main, though there is a road, there is some construction going on. So because of that, this edge is actually weights 5, which means it takes 5 minutes from Young to go to Main. But it could be possible that from Young, if we need to go to Queen, it only takes 1 minute because there is no construction. And from Queen, there is an edge going to Main that also only takes 1 minute because there is no traffic. So in this case, because this edge contains higher weight, if we have to choose the shortest path between Young and Main Street, it has to go through the Queen Street. And this would be the concept of a weighted graph. This is really powerful, especially for GPS system and the shortest path that we have to create between any two edges. Like Google Maps use this like crazy. Now there is also another concept of unweighted edge, and unweighted edge is basically an edge that does not have any parameter. So let's say that I'm creating a graph of just friends. So currently A is friends with B, and B is friends with C, and C is also friends with A. So in this case, I don't need to have any weight on the edge. They are all just friends and none of them are best friends. So that's why it's a common relationship, and we can do whatever we want to do. Then there is also concept of cyclic graphs and acyclic graphs. So cyclic and acyclic both means the same thing. Essentially, this is a cyclic graph, and let's say that if I did not had this edge in this case, then this would have been an acyclic graph, where cyclic graph means that there exists a cycle between the nodes, and acyclic graph means that there are no cycles happening. So usually in acyclic graphs there is a very popular concept of DAG, which means directed acyclic graph. And directed acyclic graph means that every single node has a directed edge. So let's say that this is node A is connected with node B, and node B is connected with node C, and C is connected with node D. So this is an example of directed acyclic graph, where we see bunch of different edges, but there are no issues with the graph. Now, because graphs are a little bit trickier, we have to take care of two things. We have to take care of vertices, and we also have to take care of edges to represent that what graph is connected with which. So that is why even in order to represent a graph, we need to have some different set of data structure. So one possible data structure is an adjacency matrix, and another possible data structure is an adjacency list. So I'll give you an explanation of both of them. Let's just have a demo graph that is simple enough. So let's just say we have a graph that A is connected with B, and B is connected with C, and C is connected with D. And this is a graph, right, that we are trying to represent. So if we have to create an adjacency matrix, what adjacency matrix means is that we are actually going to have a 2 by 2, or sorry, M cross N matrix, where for every single vertices and edges we are going to have a matrix looking like this. So we are going to have rows A, B, C, D. Same way we are going to have columns marked as A, B, C, D. Now currently all of these four values will always be 0, because node cannot be connected or cannot be its own neighbor. Now let's say that currently A has a connection with B. So we are talking about node A and its neighboring edge to be B. So in this case we would mark this value as 1. Now B has a connection with C. So node B has a connection with C. So we would also mark this value as 1. C has a connection with D. So C to D we would mark it as 1. And D does not have any connection, which means this is going to be 0. And all the other values, they are going to be marked as zeros because they don't represent anything, which means currently we have a graph that contains 4 nodes A, B, C, D. Amongst these 4 nodes, we only have connection between from A to B. So that is why this is 1, but we do not have a connection from B to A. So that is why this is defined as 0. Let's say that rather than this being a directed graph, if this were to be an undirected graph and we only have edges like these, in this case, in our adjacency matrix, we are going to represent values differently, where even from B to A, we are also going to mark as an edge. Same way from C to B, we are also going to mark an edge, and same way D to C, we are also going to mark an edge over here. So all of these values would also be 1 in this case. So this is the way on how we can represent graph in the adjacency matrix. Now adjacency list is a little bit different, where adjacency list we actually have a hash map. And I know I haven't talk about hashing yet, but inside a typical hash we have two values. We have a key and we have some value associated with that key. So as a key, we are actually going to have the 4 vertices that we are given. So in this case, it's A, B, C, and D. Now for this, we are going to mark that what are all the neighbors that A is connected with. In this case, currently A is only connected with B. So we are going to have a value like B associated for A. Same way, currently B is actually connected with A and C both. So for B, we will have a value of A and C both. And this is actually going to be a linked list which represents that there can be n number of children associated with or n number of neighbors associated with a single node. Same goes for C, that from C it is connected with B and D is only connected with C. And this is how it would be represented in adjacency list. Now the question is, which one is better and which one is worse? Well, in my opinion, both does the job well, but if you're dealing with a low number of edges, then in that case, it makes sense to use an adjacency list because it uses less space. Meanwhile, over here you see that there are more zeros than the number of ones. But let's say that we have a bunch of different edges that we are trying to work with, something like this. In this case, it would make more sense to use an adjacency matrix rather than using adjacency list. So these are the two ways on which we can actually use to represent graphs. Now, what are the operations we can do on the graphs? Speaking of operations, well, the common operations are always going to be there. That in terms of operations, we would be able to insert, we would be able to delete, we would be able to modify, we would be able to search. There is very little concept of sorting in this case because it is not very optimal for sorting. But apart from that, these are all the things that we can do. But in order to do that, we can only do it by traversing over the given graph, because we would not know that where we are traversing. So we must have to traverse, and for traverse we actually have two options. We have the breadth first search and we have the depth first search. So I'm going to talk about both of them in a simplest manner. If you want to know more about this, I have created an entire separate videos on these two topics, and they can be a video of 1 hour on its own. So that's why let me give you the basic idea that BFS represents breadth first search. What does breadth first search means? That we are actually going to search our neighbors first before going to their neighbors. And DFS means that depth first search. What does depth first search means? That we will pick a neighbor, then we will pick one more neighbor for that neighbor, then we would pick one more neighbor for that neighbor, and we would keep on moving forward in that direction. So let's try to see that in action. Let's say that we have a graph that looks like this, where we have a bunch of different nodes that are closely connected with each other, and we are trying to find some particular value, right? Let me draw out a bunch of different edges, and with every single edge, we would be able to reach to a certain conclusion about the given graph. Now let's say that this is the graph currently we have, and we also have a cycle in it. Now we are currently located at this node number A, and we are trying to find this node number B, and all of these nodes, they can have their own subsequent separate values. So if we are going in the BFS manner, breadth first search manner, what we will start to do is, let's say that this A is also the root node, because even just like trees, graphs also have the concept of root node. So let's say that this A is the root node. So from this A, we know that what are the neighbors of A through either adjacency list or adjacency matrix. So we are going to use that information, and we will start traversing to all the neighbors. So first we will go to this neighbor. Okay, this is not value number B. Then we will go to this neighbor. This is not value number B. Then we will go to this neighbor. This is not value number B. Then we will go to this neighbor. Then we will go to this number. We excluded all the possibilities for all the neighbors. None of these neighbors were actually value number B. So then we will pick one neighbor at random, and we would keep on moving forward. So let's say we pick this neighbor, again we go to its neighbor, and again we go to its neighbor. None of these yielded any particular good result. So what we do, we backtrack in that case, and again from this A we would pick another neighbor. So let's say we pick this neighbor this time, and through this neighbor we would go to this neighbor, and we would also go to this neighbor, and we found out value number B. So we can say that, okay, this is the connection between A to B, and let's just say for this example, the value of this neighbor is node number C. So we can say that there exists a path from A to C and from C to B where it is connected. Now this would be the strategy for breadth first search. And I hope that my explanation was clear enough so that you get the idea. Now let's see that what would happen in the depth first search scenario. So in the depth first search scenario, we will pick one neighbor, and we will keep going deeper and deeper into that neighbor. So let's try to understand this with an example. Suppose we are again located at this position number A. So from this position number A, first we will pick a neighbor. So let's say we pick again this neighbor. Now again for this neighbor we would pick one more neighbor. So one more neighbor, now we concluded all the possibility that this neighbor does not have any neighbor that we haven't visited. So what we would do is we would backtrack to this position, again see that are there any neighbors that we haven't visited. So we actually check this neighbor. Okay, this one we haven't visited, so we visit that, and that also did not yield any results. So again we backtrack, we come back to our main A. Then we pick another neighbor. So let's say in this case we pick another neighbor called C. From the C we again go to deep. Okay, so this one did not yielded result. So in this case again we check for this one, and this one yielded the correct result, and we again created a path from A to B to C, and again we got the correct answer. Now you must know that under which situation you need to use breadth first search and under which situation you need to use depth first search. Let's say that you have a graph and you expect B to be somewhat closely to your current A. If you expect that, in that case it would make more sense to use breadth first search, because you are more likely to find a result within some of the neighboring graphs. But let's say that you have a graph that is much more complicated and B can be located somewhere down the road, somewhere very far away. In that case it would make sense to use a depth first search rather than breadth first search. In either case, the time and space complexity for both breadth first search and depth first search is actually going to be big O of m cross n, where m can be the number of vertices and n cross be the number of edges. So it would be big O of vertices multiplied by edges, and all the operations we defined for the arrays, they are also going to have, or they are also going to follow the same time complexity, that whenever we need to find any two values, it is going to be the same. Now let's see that what are the use cases when you have to use graphs. Number one use case is actually social network. So in social network we know that, let's say that my name is person A. So person A can be friends with many other person. So I can be friends with B, I can be friends with C, I can be friends with D, I can be friends with E, something like that, right? And E can have their own separate friends. So E can have friends F and Z and all of that. Now this is how a typical social network looks like, and that is why it is really common to use that. Let's say if I'm using a social network like Facebook, where if I can only be friends with someone if that person is friends with me. In that case there would be an undirected relationship. But let's say if I'm using something like Instagram, where some X person can follow me but I cannot follow that X person. So in that case, let's say that I have a relationship like this, where X is following me but I am not following back X. So in this case we have a directed graph or a directed relationship, but either cases it works perfectly fine. Next, there would be a great use case for different internet, and because in the internet we have many different web pages that contains lot of information, and we have the HTTP URLs that are connected with each other. On top of that, from every single web page, we can also have many different HTTP web pages that connects to some other web page, and from that it can have many different web pages that connects to some other web page. So in this case, graph can be a good way to store all of that information. Plus, I already mentioned that if you want to create a GPS system or any navigation system, graphs are a wonderful approach, and you cannot build a navigation system without using graphs, where cities or places are treated as vertices and the roads are treated as edges, and that is how you move forward. On top of that, wherever you have to resolve any dependencies, you can actually use graphs to resolve that dependency. So let me give you a quick example. Let's say that you are studying in a university, and in the university we know that we can only take courses that are like 204 or 205 if we already completed its prerequisite of 105, something like this. So if that relationship is done, if unless I have completed this, I cannot move forward to this particular course. So in that scenarios, treating different courses as vertices and connections with them, between them, or dependencies between them as edges would yield to greater success in terms of all the results. So these are all the operations and all the things where you must use graphs and where they are very useful. Now the last topic comes is the hashing. So hashing actually means that hashing is actually a mechanism rather than a data structure. And what does this mechanism refers to? It refers to us finding things faster. So how do we find things faster using hashing? Well, if you have ever used a dictionary, you know that whatever word you are trying to find, all you need to do is you just need to go to that particular page that where that word starts with and alphabetically keep on going in the same direction. Let's say that if you want to find the word rat, then what you would do is first you would go to a dictionary page that starts with R, and then because A is the very first alphabet, you will start looking for A, and eventually you might encounter some words like rap or rare or something like that before finding out rat, and then you can locate that quite easily and very quickly. But let's say that if this rat was just put down somewhere randomly and without any of this dictionary mechanism, how difficult would it be to find the rat? It would probably take days. Meanwhile, because we have a structure like dictionary, you can actually complete this in just few seconds. So this is the real power of hash table or hash maps. And how it works is that I mentioned earlier that typically every single hash map has actually two items. It has a key and it has a value. Now in this case, in our example, this whole words that are currently present inside the hash map or inside the dictionary actually represents the value, and this R A T actually represents the key. So what would happen is that first we would go to place starting with R, and inside the R we would find all the values that are again alphabetically sorted. So over here we will try to find RA, and then we would try to find RAT, and it would become very easy for us to find that value. Same logic is being used to store different values inside the hash map as well, and hash maps are great at a lot of things. If we see time complexity for all the operations, let's say that if you want to search something, well, searching becomes a constant time operation. If you want to find something, or if you want to manipulate something, or if you want to change something, this can also be done in constant time. If you want to insert something, this can also be done in constant time. So this is great at a lot of things. The only issue with the hash map is that the space is a little bit extra that it consumes, but you can always tolerate or take care of space complexity, but time complexity saving is going to be huge. Same concept is with hash set, but with hash set the difference is that rather than having a key value pair, it only consists a similar type of information in the single portion where you only have like a group of people. So let's say that if I have a class, and if I have if I'm trying to find the information about roll numbers, so for the roll numbers I can actually see that, let's say I want to distribute chocolates, right? Now all the kids are sitting in the random manner. So what I can do is I can go to first child. I can ask that, okay, what is your roll number? He says that, he or she says that my roll number is 23. What I can do is I can put this value inside the hash set that roll number 23 already got the chocolate, and then move on to the next value. So in that case, no two children would ever get the chocolate multiple times, because every single time I would check that rather than giving a chocolate, let's say this student is roll number 45. So I will say that, okay, did 45 already received the chocolate? The information is not present in the hash set, which means that 45 did not receive a chocolate. So I would give him a chocolate, and then I would add value 45 over here, and that way I can use hash set to take care of unique entities. And that is also a benefit of hashing function, and also a limitation that there cannot be any duplication. So whenever you have to deal with duplicated entries, you cannot use hash map or hash set, but apart from that you can use them in all bunch of different places. And this is the real strength, and there are a lot of use cases of hashing that you can actually do it in like fast search, and then also storing the information, also storing the graph information, and bunch of different things, maintaining a file system, maintaining or building a cache system. So all of these things, hashing is great at that. So this basically concludes my what I wanted to mention regarding all of the things related to data structures. So I personally hope that you find this video useful. Let me know in the comments what are the things I could have done better, or what are the things I did not do well, or I did do well. Whichever you feel, I am always looking forward to hear more opinions on the work I'm doing. I'm a big believer in critique of all the work that I do. And yeah, hope you find this video useful. Thank you.